Good morning, students. Today we will continue with the reactions of alkyl halides. We have divided the reactions of alkyl halides into three categories. The first one is nucleophilic substitution reactions, which we have already discussed. The second one, elimination reaction, and the third one is reactions of alkyl halides or haloalkanes with metals. Today we will discuss the third type of reaction, that is reactions of alkyl halides or haloalkanes with metals. Now this reaction of alkyl halides with metals can further be subdivided into three categories. The first one is Wurtz reaction. The second one is reduction of alkyl halides. And the third reaction is formation of Grignard reagent from alkyl halides. Now we will discuss each one of these reactions in detail. So let us discuss Wurtz reaction. Now this Wurtz reaction involves the formation of alkanes from alkyl halides in the presence of metallic sodium and dry ether. We will take alkyl halides, preferably alkyl bromides or alkyl iodides. So 2 molecules of sodium iodide is given out. And the reaction takes place in the presence of dry ether. So we will get RR plus 2 NaI. So what is this RR? This RR is alkane. Now in Wurtz reaction, we will synthesize alkanes containing even number of carbon atoms. And preferably we synthesize symmetrical alkanes. Now let us discuss some examples of Wurtz reaction. Methyl iodide plus 2 sodium in the presence of dry ether will give us ethane plus 2 sodium iodide. Now, instead of CH3I, if I change this to ethyl iodide, CH3, CH2I plus 2 sodium, again another molecule of ethyl iodide in the presence of dry ether will give us butane. See, CH3, CH2, and this C will get connected to this C. So we will get CH3, CH2, CH2, CH3 plus 2 NaI. Now, see, when you are starting with one carbon alkyl halide, you are getting an alkane which contains 2 carbon. When you are starting with 2 carbon alkyl halide, you are getting an alkane which contains 4 carbon. That means Würz reaction is a very good method for ascending of series. Now let us jot down the points of Würz reaction once again. The first point is this. This Würz reaction involves the conversion of alkyl halides to alkanes, and this alkanes should contain even number of carbon atom, and we prefer here symmetrical alkane. And what about the alkyl halides? The alkyl halides are preferably alkyl bromides or alkyl iodide. Now what is the metal that is used in Würz reaction? Sodium. And what is the medium? Dry ether. Now this Würz reaction helps in ascending of series. And remember that the possible mechanism of Würz reaction is said to proceed through free radical intermediate. Our second reaction is reduction of alkyl halides in the presence of reducing agents. Reduction of alkyl halides. Rx, this is nascent hydrogen. This nascent hydrogen is provided by the combination of zinc and HCl. So what we will get? We will get RH plus HX. So this journey from Rx to RH is reduction. Here we have taken metallic zinc and HCl. We can also take tin HCl, or the combination can also be zinc copper couple in the presence of alcohol. You can also use nickel hydrogen or lithium aluminium hydride. Then we have already learned the conversion of Rx to RH using this combination Hi and red P. Our third reaction is a formation of Grignard reagent from alkyl halides or haloalkanes. Let us take this example. RBr, that is alkyl bromide. If you treat alkyl bromide with magnesium metal in the presence of dry ether, we will get RMgBr. Instead of RBr, if I write Rx, it's a generalized form, plus magnesium in the presence of dry ether will give us what? RMgX. Now this RMgX, this is known as Grignard reagent. Now in Grignard reagent, we will see that we have carbon-magnesium bond. So Grignard reagent is a very good example of a special class of compound known as organometallic compounds. So carbon-magnesium bond, magnesium is a metal and carbon is a key element in organic chemistry. So organometallic compound. And this RMgX, that is the organometallic compound involving magnesium, is known as Grignard reagent. Now this Grignard reagent, that is RMgX, for example, CH3MgX. Now this bond, carbon-magnesium bond, is highly polar in nature. So this bond is highly polar. Now why this bond is polar? This is because magnesium is electropositive in nature. That means if you compare carbon and magnesium, then carbon will be more electronegative than magnesium. So here carbon or the alkyl group will act as the negative dipole, whereas magnesium is the positive dipole. So here carbon, that is the alkyl carbon, will act as the negative dipole and magnesium as the positive dipole. So this bond, alkyl magnesium, or we can say carbon magnesium bond, is strongly polar in nature. Now the conversion of haloalkanes or alkyl halides to Grignard reagent illustrates a very important principle in synthetic organic chemistry, and the principle is known as reverse polarization. Now let us see what is this reverse polarization. Now Rx, that is alkyl halide, here X, that is the halogen, is more electronegative than carbon. So here R, or the carbon, is the delta positive 8 or positive dipole, and X is the negative dipole. As soon as you are converting Rx to RMgX with the help of magnesium in triether, you are getting Grignard reagent. Now in Grignard reagent, this R is delta negative and this magnesium is delta positive. So see this journey, Rx to RMgX. Here there is reversal in polarity. So this conversion is known as reverse polarization. So today we have learned the reactions of alkyl halides with metals. Our last reaction was the preparation of Grignard reagent from alkyl halides. In our next class, we will study some of the synthetic applications of Grignard reagent. Thank you. Have a nice day.